let's talk about how temperature affects the solubility of liquid solutions, and then in a minute we'll talk about how it affects gases dissolved in liquids as well. But to start off with here, when we're looking at solids being dissolved in a liquid, for almost everything, as you increase the temperature of the solution, the maximum solubility increases, or really just the solubility increases. The amount of stuff that can be dissolved for every 100 mils in the case of this particular graph here, or 100 grams, which would be the same as 100 mils, essentially. The amount of stuff that would dissolve in that amount of water increases for practically everything. Now you do see there is one exception to this here. This is the cerium sulfate. I believe the reason that this is an exception is because this is one of those very rare molecules where entropy actually does not favor this to dissolve. If you remember from video 2, I think, that we did in this chapter, we talked about how entropy nearly all the time favors things dissolving, and we are just going to pretend like it all the time wants things to dissolve. I believe this is one of the exceptions to that. And we'll talk about why entropy doesn't like certain salts dissolving in a later video. But again, for our purposes, because it is the vast majority of solutions that entropy favors, we are just going to go ahead and pretend, just keep it simple for our purposes here, that entropy always is going to favor things to dissolve in water. And so as you increase the temperature, things are going to become more soluble in water. And you probably are at least kind of familiar with this if you've ever made really any kind of a drink at your house where you had to dissolve something in water. The most common example of this would probably be Kool-Aid, where you had to dissolve a solid in water. So if you've ever made a pitcher of Kool-Aid, you know you have to measure out the cup of sugar, and then you have to dump in the Kool-Aid packet, and then you want to mix it up. And if you're like me, you want to immediately drink it, because that's why I'm making it. I, for some reason, very rarely have the foresight to make these things beforehand, and so I'm like, I want to drink. I guess I'll have some Kool-Aid. Oh, that's right. It's not cold. It's not even made yet. And so what I usually end up doing is I will put my sugar into the pitcher, and I'll put my Kool-Aid in, and then I will put at the coolest lukewarm water in and fill it about halfway up. Because I know that if I put really cold water in there and try to dissolve the sugar, I'm going to be stirring that thing for like 5 minutes. Maybe that might be a slight exaggeration, but it'll take a long time of stirring to get the sugar to dissolve in very cold water. Things just don't dissolve in cold water as easily as they do in warm water. And so I will put in some lukewarm water, get the sugar dissolved in there pretty quickly in that half-ish half amount or so of the water that I need, and then I'll just fill the rest with ice. And if the water is warm enough, the vast majority of that ice melts very quickly, cools down the whole thing, and now I have ready-made Kool-Aid at the proper temperature. But the key thing there is that warmer water at the beginning really helps you dissolve the material faster, because things just dissolve in warmer water better. Not only can you get more stuff into warmer water, but things will dissolve faster in warmer water. When you're talking about gases dissolved in water, though, the same does not hold true. It's actually the exact opposite for gases. So the warmer the temperature, the more solid you can dissolve in a solution. but the warmer the temperature, the less gas will dissolve in a liquid, specifically water in this case. As you increase the temperature, the gas molecules actually have more energy, which makes sense because it's at a higher temperature. Because they have more energy, it's easier for them to escape. Essentially, they're in a sense trapped in the liquid, but they don't really want to be trapped in the liquid. They're gases. They want to be free. They want to roam around. They want to be free to move large distances before they bump into something else. And when they're trapped in that solution, they're going to, even though I'm kind of pretending like they're sentient, but they aren't really. But in a sense, the gas wants to escape as quickly as it can. And so if it has more energy, it can do that more readily. And so the warmer the solution is, the faster those gases escape. This is why if you've ever had the great displeasure of pouring a warm soda, you notice that you start to pour it and the fizz goes all the way up to the top, and maybe you manage to not have it drip over, and you're like the little meme guy, like, yes, success, didn't spill over the top. And then you watch the fizz go down and your liquid is here. Like you have nothing. Like it's like you poured absolutely nothing in there. It's because you were pouring that warm pop, and as you're pouring it, all the carbonation in the pop is escaping rapidly. Because not only is it warm, but the actual physical process of pouring also gives the CO2 a chance to escape, because it's carbon dioxide that is in the solution there that gives it its fizziness. Whereas if you pour a very cold soda, you're still going to lose some. There's still going to be some CO2 that escapes, but it's not going to be nearly as bad as with the warm soda. And just in case you were wondering, no, it doesn't really help to pour it over ice. I'm sure it helps a little bit, but it's like, without the ice you lose 90% of the carbonation, and with the ice you lose 80% of the carbonation. Like it's not, doesn't help all that much. So the moral of this story: only pour cold pop. Don't pour warm pop. Cool it down first. And also, greater the temperature, the less the gas solubility. Alright, and so this is kind of just the same thing here again, just talking about the example of a can of pop this time instead of pouring out of a 2-liter. Cans of pop are manufactured under, I want to say like 4 atmospheres of CO2. I don't think it's crazy high, but it is decently high pressure CO2. And that keeps a whole bunch of CO2 molecules in solution because it's under that really high pressure. And then when you pop the top and you hear that sound, that's the release of the pressure, now all the CO2 starts to bubble out because it's no longer at that high pressure that it was before. And so you have a limited amount of time to drink that pop before it tastes nasty. All right. Real quick here before we call it for this video, let's talk about the equation that can be used to actually quantify the solubility of a gas in a solution. This is what we call Henry's law. The S sub gas here is the solubility of the gas, and the solubility is measured in moles per liter. It's a solubility just like anything else, just like the solubility of a solid in a liquid would be. It's the same thing, just how much stuff can go into what volume. So moles per liter is the units on the solubility. It is equal to Kh, which is a constant. This is called Henry's constant, or Henry's law constant, times the partial pressure of the gas over that liquid. So what is the pressure of the gas that is in contact with the surface of the liquid? The Henry's law constant here is going to be different for every different material. I will point out here on this slide this is a typo here. That should be -1, I believe. You can double check me by Googling it just to be sure. But I know for sure it's not +1. That actually is physically impossible. That would be, this is essentially saying that you can fit 58 moles of ammonium into 1 liter of water, which is not actually physically possible. So I know for sure that +1 is not correct. I believe it's -1 is the correct thing here, but you can double check me just to be sure on that. And so this equation is pretty straightforward. It's pretty simple, so we're not going to spend a whole lot of time on it just because it is so simple. It's just the solubility is equal to the constant times the pressure, but it is still fairly useful, especially if you're someone that's going to be working with solutions like this. If you're someone that is planning on going into, for example, environmental chemistry, this will actually be very useful to you. So if you're ever trying to work out how much of maybe some kind of a smog molecule or something is being dissolved into a stream or something, if you know what the pressure, like how much of those molecules there are in the gas, in the air, you could work out how much of it is going into the liquid solution as well. So speaking of that, let's go ahead and do an example here. So this is example 11.1 from your book. It says, at 20 degrees C, the concentration of dissolved oxygen in water exposed to gaseous oxygen at a partial pressure of 101.3 kilopascals, which is 760 torr, which, by the way, is also 1 atmosphere, is 1.38 times 10 to the -3 moles per liter. So that would be the solubility. Use Henry's law to determine the solubility of oxygen when its partial pressure is 20.7 kilopascals, which is 155 torr, the approximate pressure of oxygen in Earth's atmosphere. So this question is actually assuming that we don't have this data, I believe. Oops. I believe the question is assuming we don't have access to the constants. So we're going to go ahead and work this pretending like we don't have that, like we don't have the constant. So we are given the concentration of dissolved oxygen in water, and maybe one of the trickier things about this question is just realizing that when it says this is the concentration of oxygen, what it's really saying is that is the solubility of the oxygen. That is this. So just being able to recognize that when it says this is the concentration of the gas in the liquid, that is the same thing as saying as this is the solubility of the gas. That might be the trickiest part of this question. So you have the solubility of the gas is given to us there. We're also given the pressure, which is this part. And so this first sentence here is really just giving us everything that we need to find the constant all on our own. Again, assuming that we're pretending like we don't know this here is here and exists. So let's go ahead and set that up and see if we can solve that. So we're told that the concentration is 1.38 times 10 to the -3 moles per liter. And we are given, and actually the constant that we have over here, since I know the conversion, and actually you would know it too since you hopefully did this in Gen Chem 1, they didn't actually give us the pressure in a unit that matches with what we have on the previous page, but I'm going to go ahead and just change it over to 1 atmosphere, just because I prefer to work with it. Actually, no, I can't do that, can I? Because the information they give me in the next part is in torr. So we'll go ahead and keep it in torr. Never mind. So we are trying to find KH here, and we're told that we are at 760 torr. So then if I solve that for the constant, let's see what I get. 1.38 times 10 to the negative 3 divided by 760 torr. The constant would be, let's see, 1.82. We'll just cut it off there. Times 10 to the negative 6 molar per liter torr would be the units on that. Okay. And actually, I shouldn't have put the liter there. Sorry about that. It would just be molar per torr. Over here, that should have been moles, because moles per liter is molar. So if you prefer, you could have moles over liter torr. Either way is going to work and just be fine. So then the last step here, we're trying to find the solubility now at this point. So remember, the solubility of O2 is equal to the constant times the partial pressure of O2. We now know the constant, and we are given the pressure in that second sentence there. So we have both of these parts, and so we can just solve for the solubility. So that is going to be 1.82 times 10 to the negative 6 molar per torr. Multiply that by the pressure, which is 155 torr. And that will give me, let's see, I'll put this in scientific notation, 2.82 times 10 to the negative 3 molar. Okay. So that is the pressure, or the concentration, I should say, of oxygen in 20 degrees C water if it's exposed to the atmosphere. All right, we'll call it there for this video. In the next one, we will talk about some different ways of expressing the concentration of something other than just molarity, which we discussed in Gen Chem 1. So I'll see you in the next video.